So what is time? If you're a physicist, you probably have like an internal model of what time is, and that's probably sufficient for the applications that you use time for. But if you're trying to tell a computer what time is, as we're trying to do in this open source project called PhysLean, whose aim is to digitalize or formalize physics into an interactive improver called Lean 4, then you have to be very specific about what time is. So how do we define time in the project PhysLean? We do it by thinking about what sort of structures time should have. And the first structure time should have is that it should be smooth. And this is kind of an assumption that we make throughout physics. It's the assumption of smoothness, that everything should be nice and smooth. There's no weird discontinuities or weird things that are jagged that happens in the world. Everything is sufficiently smooth. To a mathematician, this is the assumption that time has the structure of a manifold. So in PhysLean, we obviously give time the structure of a manifold. And this manifold is equivalent to the real line. So it's equivalent to R. You could say it's exactly the same as R, but that is perhaps less mathematical than saying it's equivalent to R. The second structure we expect time to have is an orientation, a backwards direction and a forwards direction. So we give in PhysLean time the structure of an orientation. And we do this within this type called time man. And what time man is in PhysLean, it is the type that carries precisely those two instances. The instance of a manifold and the instance of an orientation on that manifold. There's something else that we assume about time, or another structure we think time should have. And that is that time now should look the same as time in the future or time in the past. In other words, time doesn't change when you move points in it. And mathematically, this corresponds to the statement that time has an action on it, something called a transitive action. In other words, you can take one point to every other point with this action of a group, and that group is obviously the real numbers. So in the type time trans man, corresponding to time with transitive action, that's a manifold, we define this notion of time with the structure of the transitive action, the manifold structure, and an orientation. Now, this notion of time has no concept of a distance between times on it. There's no way in this notion of time or in this type time trans man to say that to take two times t1 and t2 and go, you know, there's 10 seconds between them. That doesn't make sense because this notion of time doesn't have the structure of something called a metric. A metric on a manifold is the mathematical object that gives that manifold a notion of distance. It's the thing that says you can take 2 points and you can give me a real number that corresponds to the distance between those 2 points. So we naively, or really, we want time to have that structure. And we want it to be nice and to behave nicely with respect to this transitive action that says, you know, time now should be the same as time in the future, and that should be the same as time in the past. And if we look at all of the choices of metric on time trans man that obey the transitive action, we'll notice that there are a positive real number of choices. And a choice of one of those metrics, a choice of one of those positive real numbers, corresponds to a choice of units. For example, seconds, minutes, days, years, microseconds, picoseconds, etc. So if you choose a metric on time, then you get a choice of units. And given such choice in metric, you can start to do things like you can take time now and you can add 10 seconds to that. Or you could take 2 times and work out the distance between them in years. This choice of units corresponds to a choice, this choice of metric corresponds to a choice of units. And to say something has dimensions of time is really a statement about how that quantity changes when you change the units, when you choose a different metric on time. So within PhysLean, we don't give this type time transman a metric. What we do is we say there is another type, time. And this type has the notion, has the structure of a vector space. So it's not a manifold anymore. It still is a manifold, but it's more than a manifold. It's a vector space. And to get from time transman to this type time, you define a unit and a theorem. So you just say there is a point in time that I'm going to call 0, and you can choose any point to be 0. And you say, I'm going to choose a unit. And once you've done that, you can map this time transman down to this other type called time, which has the structure of a vector space over the reals. And really, when a physicist is working with time, they've implicitly chosen a unit and a 0 of that time. And as such, they are really using this type time in PhysLean. So that's how we define time. That's how we define time within the project PhysLean, is how we define the notion of a unit of time in PhysLean and the dimension of time in PhysLean. If you have any questions, feel free to either add them to the comments below or get involved in the discussion of this project on the Lean Tulip. There's a PhysLean channel where these conversations about the project happen.